Now let's take a look at two tools provided in SpectracyberRPi for filtering your data. We're first going to look at the notch filter. The notch filter is used to remove any kind of spurious noise. Just be advised that you will be modifying your data if you do this. So the wise thing is to be certain that that the data is indeed a spurious outlier from the data source. And usually it's a spike, could be caused by some object passing through your beam, like an airplane or a bird or something, or maybe a noise picked up from the local environment. The second one, of course, is the Butterworth filter, which is much more useful. It will help you reduce some of the random noise in the signal, and you can choose different Nyquist cutoff frequencies in order to improve the quality of the signal. It's very, very useful for you to clean up a noisy signal. However, once again, you are modifying your data, and this may not be a good scientific method, but it's up to you. The tools are provided. Use them wisely and use them correctly. Let's go ahead and take a look now at these two tools. Okay, let's go ahead and take a look now. So what we're going to do is click on Tools, and from Tools we'll click on the RFI notch filter, and I'm going to go ahead and just use our temp data that we've used before. This isn't the best choice, but just to give you an idea how the notch filter works. Normally, let's assume that this pulse here happened to be actual bad noise. Normally it'd be a small little spike someplace on the curve, but I'm just going to go ahead and do it. Now it says use the 2 mouse clicks. We've seen this before. So I'm going to click on the left hand side, get a little red dot, click on the other side, and you'll see what happens here is that it's immediately selected that region with red dots, and now you notice at the bottom it's going to show a direct line, a straight line between the 2 bottom points. All the red dots would be removed. Over here on the notch filter selection, it asks you if you want to remove them. At that point, if you click on the yes button, you'll be given an opportunity to write a file name if you wish, or if you want, you can go ahead and overwrite the current file. But remember, you will be removing your data from that file. It's more advisable to save it under a new file name so that at least you preserve your original data in case you decide to change your mind about using the notch filter. So I'm going to click on no, and that's a simple use of the notch filter. Now the other filter again is under Tools, and this is the Butterworth filter. Now the Butterworth filter will use the same function, the same data, and I'll do it for you're allowed to choose a type fit here for either frequency, the universal time, or the sidereal time. The data will be fitted to a curve, and the cutoff frequency will be chosen here under the type of the cutoff. Normally you would use the Nyquist frequency. That means the sampling rate is at least twice the value of the cutoff. But you could cut it. You could even get a stronger filtering by using 3/4, half, quarter, eighth, and so on of the Nyquist filter. That means your sampling frequency is much and than the standard Nyquist cutoff frequency. But I'm going to go ahead and use the 2 here first, not the standard Nyquist frequency. So let's just go ahead and click on the OK button. You take a moment or two. It'll do the filtering, and it should pop up. And here's our filter. Now, I don't need to save this data, so we will go ahead and close it. Once again, you'd have the opportunity to save the data, this filtered data, and you should use another name because you'd like to preserve your original data. But if you want, you can, of course, choose to overwrite the original data, but it's wiser to write a different file name. So you can always redo this if you want to by using the original data. At the top, you see the filtered data. The red line is the Butterworth filtered data. You notice how it's much smoother than the raggedy blue line, the noisy blue line. The middle curve shows you where the Nyquist frequencies and the cutoff frequency, sampling frequencies are located, along with your 3 dB gain, the red line. And the blue line is the shape of the of your Butterworth filter. And the bottom shows you the power density function, so you can take a look at where it is. And you notice that the red line The Nyquist filter is way out here on the low end of the thing, and that's where it should be. All right, let's take another look at this, and let's click on it a second time on the tools. Go back to the Butterworth filter, and we'll use the same data, same original data, since we didn't change it. And click on the, this time we're going to take, say, 1/4 of the frequency of the Nyquist frequency. That's even a stronger filtering, and take a look at that and see what happens. Here's our second figure, and you can compare the two. Let me go ahead and clear this from behind it. We don't want to save it. And now putting these two side by side, you notice that it's even, the signal is even a little bit cleaner. It's a little bit smoother. It also has changed its shape. We don't have it following the curve as closely as the other one. So when you do a lot of filtering, you will change the shape of things. And you notice that your cutoff your Nyquist frequency is still inside the main band where it should be. And way down on the slope is your sampling frequency. So the sampling frequency is being pretty much attenuated, which is what you want to do in filtering. But you will be changing the shape a little bit. This may be a more realistic shape of that curve. It's up to you to make the decision. So these tools are provided for you to do what you want. And of course, if you wanted to, we could zoom these things up. Let's just do that for fun of it and see what happens. Let's just increase this size right here. Just expand it. And there you can see just how smooth the curve is. Look at the red line and how it's really smoothing out all the raggedy signals. Now I'm going to minimize this again. And let's do the other one and bring it up and see what the difference is. This is the one that was done at the Nyquist frequency. You'll see it's fairly smooth, but it does follow the curve a little bit closer. It's up to you to decide which one you want to use, but that's how we use the Nyquist frequencies. I hope you enjoyed this, and next we'll be talking about some other subjects.